this video, I'm going to show you how to use Excel to figure out probabilities associated with specific values and specific values associated with probabilities in normal distributions based on the mean and standard deviation. Now, keep in mind that in Excel, you get very precise probabilities and proportions and values, whereas in the empirical rule lecture, I used a simplified version of those probabilities and percentages, so some of them are slightly off, but really close. For example, when we were looking at the empirical rule, we were saying that 2.5% of scores are above a z-score of 2 and at or below a z-score of -2. But in reality, that's 2.28%. But again, we use simplified probabilities in the lecture. So if you're doing this in practice, you wouldn't want to just rely on the contents of the lecture and the empirical rule, kind of the basic qualities of the normal distribution. You would actually want to do this in Excel. Also, you'll notice that we're not going to be limited to looking at probabilities and proportions associated with z-scores of -2, -1, 0, 1, and +2. We can look at that for any value in Excel. Hooray! All right. So let's start by looking at an example where we have good old Theodore, and he wants to look at the download speeds in his for his app for Flight Pro, the map download speeds. So he's the owner of Flight Pro, which is the app that provides maps and real-time weather reports for pilots, and he's not satisfied with the map download speeds on electronic devices, which currently has a mean of 90 and a standard deviation of 30, and it's normally distributed. However, he has to do a demonstration of the app for a group of investors today, and they expect a minimum of 60-second download speed. He's got no time to work on fixing the download speeds, so before giving the demonstration, he wants to predict how likely the following outcomes would be. So how likely is it, if he knows the mean download speed for maps is 90 seconds with a standard deviation of 30, how likely is it that he's going to impress the investors with a mean download speed of 60 seconds or less? How likely is it that he's not going to impress the investors and have a mean download speed above 60 seconds? How likely would it be that he'd get a download speed of exactly 60 seconds, exactly 90 seconds, and then we're going to just confirm that Excel actually works by looking at the probability that his download speed would be less than or equal to the mean. So remember, if we look at a normal distribution, which is what we're assuming, the mean is in the middle. So the bottom less than or equal to 50%, right, would be below the mean. So we'll just confirm that here in a little bit. So for all of these probabilities, we're going to use the normal distribution function in Excel. And remember, the tenets of the empirical rule only apply to normal distributions, and there's really only specific probabilities or proportions in normal distributions. If you're not working with a normal distribution, then the probabilities that you get here would be slightly off or way off if your distribution's super skewed. So I'm just going to show you how just knowing the mean and standard deviation and your value of interest, you can figure out all sorts of probabilities or proportions. So check this out. Type in equals norm, not norm, norm, all right? And then look for norm.dist. When you put your cursor over this, it'll tell you it returns the normal distribution for a specified mean and standard deviation. So double click that. First, we're going to highlight our x value, or in this case, since we don't have a value to highlight, we're just going to manually type in 60. Because for the first one, we're looking at the probability that the device he uses in the demo will have a download speed of 60 or less. 60 is our mean of interest. Comma, highlight the actual population mean, or you could manually type 90 if you wanted to. Comma, standard deviation is 30. Click on that. And then we are going to hit comma again, and you'll see this cumulative function pop up. So if we say true, that means we're going to get a cumulative probability. And remember, a cumulative probability is the same as a percentile. It tells you the probability or proportion of scores less than or equal to a specified score, or in this case, less than or equal to 60. Well, that works for us in this case because 60 or less is what we're interested in looking at the probability for. So we're going to say true. If you selected false, it would give you the probability of just that exact value. So we're going to double click true and we're going to hit enter. All right, we get 0.15866, or a 15.9-ish% chance that he's going to end up having a download speed that's less than or equal to 60 in his demonstration. Now let's figure out what's the probability that it's not going to be less than or equal to 60, that it's going to be greater than 60. Well, none of those functions I showed you gives you greater than, but to get that, you take equals 1, the probability of any outcome, minus the probability of less than or equal to 60, right? So we're getting rid of the probabilities we're not interested in, and we're left with an 84.1% chance that in that demo, the download speed is going to be greater than 60. See how that worked, right? If there's a 100% chance of any outcome, and there's a 15.7-ish% chance that it's going to be less than 60, then what's left? Well, about 84% will be greater than that. I'm going to draw this for you just to make sure that it makes sense. So if we go here, our mean is 90. We're looking at 60, right? So roughly, there is about a 15.8% chance, really 0.9 if we round correctly, percent chance it'll be 60 or less, and that leaves roughly an 84.1% chance of it being greater than 60. All right, now let's move on to figuring out the probability of exactly 90-second download speed for that device that he uses in the demo. So we go equals, go to norm.dist, double click it, type in 60 for x, comma, highlight the mean, comma, highlight the standard deviation, comma, and this time we're going to say false. So double click false, hit enter. So the probability that it's going to take exactly 60 seconds to download that map is 0.008 or 0.8% chance. Let's do it for 90. Norm.dist, again, double click it. X now is 90, comma, population mean is 90, comma, standard deviation is 30, comma, and false because we want the exact probability of that exact value of 90, hit enter. So the probability that it's going to take exactly 90 seconds to download that map on that device is 0.013 or 1.3% chance. So let's think about these numbers for just a minute. Getting a mean download speed longer than 60 seconds, right here, is more likely than getting a mean download speed of 60 seconds or less. If you think about the mean and the standard deviation, most downloads are within 30 seconds of 90 seconds, or between 60 and 120 seconds. So getting a download speed of 60 seconds or less would not be as likely as getting a download speed above 60 seconds if most are between 60 and 100. So based on this, he's likely to be embarrassed in front of the investors. If we look at these values, you'll notice that they're both very, very highly unlikely. It's always highly unlikely to get an exact value, even if in this case, the value equals the mean. So now let's look at this one. So just to confirm these formulas in Excel, let's make sure that the cumulative probability for the mean, 90, is 50%. Because remember, the mean is in the middle of the distribution. It's at the 50th percentile. So 50% of score should be less than or equal to 90. So let's check it out. Equals, norm is back. Double click norm.dist. Now this time 90 is our x, comma, mean is 90, comma, standard deviation is 30, comma, and we're going to say true, cumulative less than or equal to 90. Haha, 50%. So I'm feeling good that Excel knows what it is doing. I'm going to save this real quick. All right, now let's take a look at the next example. So now we're looking at Theodore again, but we have a different kind of scenario going on. So he wants to hire a software developer to help him decrease the download speed of Flight Pro. His friend's an instructor at Full Sail University for the software development program and has offered to help him find a software developer among their graduates from the last year. So over the past year, the cumulative GPA among software development graduates at Full Sail University was normally distributed with a mean of 3.0 and a standard deviation of 0.5. So initially, his criteria for considering a graduate for hire is having a GPA above 3.75. So he's curious what proportion of graduates would be considered for hire. Or in other words, what proportion of graduates would have a GPA above 3.75. So let's figure it out. Now remember, we're looking at an above situation. There's no function in Excel that gives us that, but we can figure out the proportion that are 3.75 or below, the cumulative probability, and then subtract that from 1. So that's what we're going to do here. So equals norm.dist, double click. Our x value is 3.75, comma, our mean is 3, comma, our standard deviation is 0.5, comma, and let's start with true, and then enter. So 93.3-ish% of Full Sail graduates from the software development program have a GPA less than or equal to 3.75. But we want to know how many or what percent or proportion have a GPA above 3.75. So we'll just do equals 1 minus at or below to get above. So based on this, you can see that about 6.7%, right, if we took this and turned it into a percent, which you can actually do, you can right click, format cells, percentage. Let's do it. Why not? So 6.68% of graduates from the software development program at Full Sail have a GPA above 3.75. Let's say that that's a little worrisome for him. He wants to have about 20% of graduates to choose from. So instead of focusing on a specific GPA, Theodore decides to rely on a percentile to determine the criteria for considering a software developer for hire. So he decides to consider anyone with a GPA in the 80th percentile or the top 20% for hire. So now we need to figure out what GPA is at the 80th percentile. We're going to use a different function for this, the norm.inverse function. So we're going to do equals, type in the norm again, but this time we're going to return the inverse of the normal cumulative distribution. So basically we're going to put in the probability we want and it's going to spit out an x value. So double click norm.inv. Our probability is going to be 0.80, comma, our population mean is 3, comma, our standard deviation is 0.5. Now when you're using this, it's always going to give you the value at that percentile. So if you put in 0.8, it's going to give you the value at the 80th percentile. If you put in 0.2, it's going to give you the value at the 20th percentile, or that represents the bottom 20%. So just keep that in mind. All right, enter. So if he was selecting from people in the 80th percentile, then anybody above a 3.42 GPA would be considered for hire because they have to be in at least the 80th percentile. You also know based on this that 80% of graduates have a GPA that's 3.42 or less, and only 20% of graduates have a GPA of 3.4 or above 3.42. So if we look at this, using the 80th percentile criteria would lead to the largest pool of candidates because a 3.42 is easier to achieve than a 3.75. And you know that 20% of GPAs are above 3.42, right, 80th percentile, but only 6.7-ish, 6.68% of GPAs are above a 3.75. So if you wanted to have the largest pool of candidates, you would go with this strategy. However, if you use the criteria of a GPA above 3.75, that would probably lead to the highest quality, or at least the highest achieving pool of candidates. All right. Now we're ready to move on to looking at sample means. So instead of looking at probabilities in a population distribution of population scores, we're going to be looking at probabilities associated with a sampling distribution of potential sample means. And this is more useful in terms of decision making and figuring out if interventions had an effect and doing actual research. Because usually we don't do research with a single score, we look at samples instead. All right. So now we're going to look at a situation where Theodore, the owner of FlightPro, really is not satisfied with the map download speeds on electronic devices. Remember, it had a mean of 90 seconds with a standard deviation of 30. Not loving it. He was embarrassed in front of the investors. Now he's got to do something about it. So he hires that software developer from Full Sail to reprogram the map feature in Flight Pro with the hope that the map download speeds will decrease to at least an average of 60 seconds. After the software update, Theodore takes a sample of 3 electronic devices to see how long a map of the Las Vegas airspace takes to download. So we're going to have a sample size of 3 electronic devices, and we want to figure out the probabilities associated with his desired values. So first, we're going to figure out, just due to chance, what's the probability that Theodore's sample will have a mean of 60 seconds or less? Just due to chance, even if the software update did not improve download speeds for maps. Because remember, when we're figuring out these probabilities, it's based on the original population, right? Before we did the update. So what he'll do is he'll compare what he actually gets in his sample to what he would have gotten due to chance to see if he's confident in his results. He also wants to see the probability that his sample will not have a mean of 60 seconds or less by chance. Even if the software update did not improve download speeds, how likely is it he would get a mean above 60 seconds in his sample? So let's figure it out. For this, we are going to use the norm distribution function. But remember, it requests the standard deviation. When we are looking at a sampling distribution with sample means, we're not going to give it the standard deviation. We're going to give it the standard error. So before we can use that function, we need to figure out our standard error. And that's what this space is for here. So we're going to do equals. Remember, the standard error is equal to the standard deviation divided by the square root of the sample size. So we're just going to do that here. Equals 30, our standard deviation, divided by square root, double click it, of our sample size of 3. Hit enter. Yes, we want to add the parenthesis. Thank you. All right. So just due to random chance, just due to error, even if whatever he tried to do, that update, had no effect, you would expect that your sample mean would be about 17 seconds off from the population mean. So just due to chance, you would expect that your sample mean would be between, so 90 minus this, to 90 plus this, between 72 and 107 seconds roughly, just due to chance. That's kind of the range you would expect to see for any given sample of 3 devices. So now let's figure out these probabilities. So equals, norm is back, norm.dist, double click it. Our x in this case is 60, comma. Our population mean is 90. Click that, comma. Now standard deviation is now our standard error. That's our measure of spread for means. So don't click 30, click the 17.32050808, comma. And for this, we do want to get the cumulative probability, right? Less than or equal to. So we're going to double click true. Hit enter. Now to get the inverse of that, right? We've got the probability for less than or equal to 60. To get greater than 60, we just take equals 1, the total probability of any outcome, minus the stuff we're not interested in, less than or equal to 60. Hit enter. I'm going to change these to percentages just because I like them better. So highlight, right click, format cells, percentage. Okay. So if we look at this, we can see there's a 4.16% chance, right? So think about, like, let's put it this way. So if Theodore's sample does not, or does have a sample mean of 60 seconds or less after the software update, he should be really, really confident that the update is the reason he saw the decreased download speeds, because it's highly unlikely, right, less than a 5% chance that his sample of devices would have had a mean download speed of 60 seconds or less just by random chance, even if the update did not improve download speeds for maps. So this is how likely 60 or less would be due to chance. Very unlikely. If he gets 60 seconds or less, it's probably not due to chance. It's probably due to the update working. Conversely, if we look at this, it's highly likely, right, 95.8% chance, roughly, that he would have gotten a larger mean just due to chance if the update didn't work. So that again tells you if it's less than or equal to 60, it's likely the update had an effect. It's not a difference you would expect to see no matter what, just due to chance, even if the update didn't work. Okay, now let's look at a situation where, let's say the update has already occurred, okay? And the software developer claims that the new mean download speed for Maps in Flight Pro is 45 seconds with a standard deviation of 5. So the vast majority of download speeds are between 40 and 50 within one standard deviation of the mean. So if we look at this, Theodore plans on taking a sample of 30 devices and he wants to test the software developer's claims. So he wants to take a sample of 30 devices and he wants to see and anticipate how likely the likely mean download speed that would occur if the software developer's claims are accurate. So specifically, he wants to look at the middle 95%. So he's going to take a sample of 30 devices to test the claim, and he's trying to anticipate the likely mean download speed, or the middle 95%, that would occur if the software developer's claims are accurate, if it's really what happened. So what we're going to do is we're going to use the confidence interval formula to figure out the middle 95%. So I'll show you how to use that. So we go, first of all, equals. So you want to be right here. We're going to find out the total standard error. So not the standard error in general, for just one standard error, but the standard error associated with if we looked at the middle 95%. Because if we just did the normal standard error, the standard deviation divided by the square root of the sample size, that would tell us that what one standard error is. And that would be kind of roughly relative to the margin of error for the middle 68% of the distribution within one standard error of the mean. But we want to expand that to the middle 95%. So instead of having you use the mean formula with z-scores associated with the z-score at that location, we're going to use this confidence interval formula. So here we go. Equals confidence.norm. Double click it. Alpha is simply 100% minus the middle you want to look at. So 100% minus 95 would be 5%. And when you put this in, you put it in terms of p. So 5% would be a p of 0.05. So again, if this was converted into a p-value, it would be 0.95. And 1 minus 0.95 is 0.05. It's kind of like what's left, the remaining percentage or probability. All right, comma. Standard deviation, actually select the standard deviation because the formula takes the standard error into account. You don't have to do it yourself. So click on that expected standard deviation, what the developer claims, comma, the sample size, 30, enter. So within the middle 90%, you would expect the margin of error of about 1.789 if the claim is accurate. So now let's figure out what the middle 95% would be by doing equals the mean minus that level of error equals the mean plus that level of error. So we would expect between 43 and 47-ish seconds if the claim is accurate. Let's go ahead and visualize this real quick. So if we go here and we look at the middle 95%. And of course the midpoint in this is 45 according to that software developer. So we'd have like 43.2 and 46.8 right here. So if the software developer's claims are accurate, the mean is actually 45 with a standard deviation of 5, there's a 95% chance that the mean download speed for randomly selected 30 devices would be between 43.21 and 46.79 or 46.8 seconds. So if Theodore took that sample and got a mean between 43.2 and 46.8, he should trust the software developer's claims. Now I want you to note that the probabilities presented in the empirical rule from the lecture are not exact. They're simplified. Because technically, if we were looking at kind of what you saw in the lecture with a z-score of -2 and +2, technically this is 2.28%, and this is 2.28%. But again, the visualization of the empirical rule that's often used and that I use in my lecture tries to simplify this by just rounding to 2.5%. So if you did this math using x equals -2 times standard error plus the mean and 2 times standard error plus the mean, you'd get slightly different values. These values are more accurate. All right, so now Theodore wants to more precisely estimate the download speeds if the software update had an effect. So after this update, again, that software developer is claiming that the new mean download speed for Maps on Flight Pro is 45 seconds with a standard deviation of 5. Theodore plans on taking a sample of 30 devices to test this claim. And again, he wants to more precisely anticipate the likely mean download speed in the now middle 50% of devices that would occur if the software developer's claims are accurate. So here we go. We're going to do the confidence interval formula again. So CON, confidence norm, to figure out the magnitude of error that would be associated with the middle 50%. So double click. Alpha now, 50% minus 100 is 50%, or 0.5, or 100 minus 50% is 50%, or 1 minus 0.50 is 0.50. So remember, we always put alpha in terms of proportions, not percentages. Comma, our standard deviation is 5, comma, our sample size is 30. Enter. So the middle 50%, this is the kind of margin of error you would expect there. Now let's take a look at this. Our low mean equals the expected mean minus this margin of error to the expected mean plus this margin of error. Whoa, what just happened? Let's do it again. Equals the expected mean plus this margin of error. All right, that's better. So, if the software developer's claims are accurate, there's a 50% chance that the mean download speed for randomly selected 30 devices would be between 44.38 and 45.62 seconds. So let's draw that out. Remember, this is going to be our mean 45. We've got 44.4-ish and 45.6-ish. That's our middle 50%. All right. So again, if the claims are accurate, there's a 50% chance that the mean download speed for his sample would be between 44.4-ish and 45.6-ish seconds. So if Theodore got a mean between 44.4 and 45.6, he should really trust the software developer's claims. Now notice, this is a narrower range than what we had for the middle 95% right here. And that makes sense, right? Because if you think about it, the middle 95%, so about 43 to about 47, is wider, right? And the middle 50% is more precise. So of course those results are going to be closer to the mean when you're using the middle 50% versus the middle 95%. All right, so I hope you enjoyed learning how to use Excel to figure out probabilities and proportions and scores associated with those. And it is a lot easier than doing it by hand, and it's also more precise. So hopefully someday you'll find yourself using this in some way, shape, or form, because it is a really, really practically useful tool of statistics in business.